Welcome viewers to the lecture series on integral equation under NPTEL course. From this lecture and onwards, we are going to discuss on Fredholm integral equation. You can recall the general form of Fredholm integral equation is given by phi x y x equal to f x plus lambda integral a to b k of x comma s y s ds, where a less than equal to x comma s less than equal to b, and this particular phi x actually responsible to determine the kind of the integral equation. If we consider phi x equal to 1, then we will be having y x equal to f x plus lambda times integral a to b k of x comma s y s ds. This equation is actually Fredholm integral equation of second kind, and also it is a non-homogeneous Fredholm integral equation. And in particular, if we consider here f x equal to 0, then you can find this equation f x equal to lambda times integral a to b k of x comma s y s ds. This is actually Fredholm integral equation of second kind, and it is a homogeneous Fredholm integral equation. And if we choose phi x, this is equal to 0, then f x plus lambda times integral a to b k x comma s y s ds, this is equal to 0. This last equation is actually Fredholm integral equation of first kind. Now, in case of Volterra integral equation, the Volterra integral equation can be generated from linear ordinary differential equations which was of the form of initial value problem, and this Fredholm integral equation are results of converting the linear ordinary differential equations of boundary value problem type problems to an integral equation, leads us to Fredholm integral equation. And as we are going to first work on linear ordinary differential equations and boundary value problem, so we will be landed at Fredholm integral equations. Those are linear Fredholm integral equation. So, first of all, we consider one formulation, that is construction of Fredholm integral equation from a given boundary value problem. Consider this boundary value problem d2y dx2 minus lambda y, this is equal to 0, where a less than x less than b, and given initial conditions are y a equal to 0 and y b, this is equal to 0. Consider this as the first equation, y a equal to 0 first boundary condition and y b equal to 0, this is the second boundary condition. Actually, this type of boundary condition, when specified at the two ends, that is at x equal to a and x equal to b, these are actually called separated boundary conditions. And when we will be considering the Green's function approach, then we define the general formulation of second order boundary value problem with separated boundary conditions. Now, from this given equation, if we integrate, then we can find dy dx, this is equal to lambda times integral a to x ys ds plus C1. On the right hand side you can see I am integrating from a to x, and since x is at the upper limit, so variable considered here as s, and I am writing here C1 because for the given problem there is no information of dy dx at x equal to a. So, we will determine this C1 at a later stage. So, call this equation as 4. If we integrate again, then we can write yx, this is equal to lambda. Now, these a to x ys ds, these we have to integrate within the limit a to x. So, on the upper limit x it will be replaced by s, and variables s under integral sign will be changed to s1. So, ultimately we will be having integral a to x, then integral a to s y s1 d s1 ds plus c1 x plus c2. Now, at this point you can note that this C2 I am writing here, this C2 takes care of minus C1a, and although the value of y at a equal to 0 is given, still I am writing C2 here, because using these two boundary conditions we will be able to evaluate this C1 and C2. And now, this repeated integral can be converted into a single integral. You can recall the using the formula for generalized replacement lemma. So, using the generalized replacement lemma, or you can interchange the order of integration, you will be getting this result integral a to x x minus s y s ds plus c1 x plus c2, call it 5. So, this last expression we are getting from the previous one by applying generalized replacement lemma. Now, if we use the condition 2 y a equal to 0 in 5, then we can find that y a, this is equal to 0, equal to contribution from this integral will be exactly equal to 0, because we are integrating from the range a to a, because x will be replaced by a. So, a to a minus s y s ds, this is equal to 0. So, we are only left with c 1 a plus c 2, and this implies c 2, this is equal to minus c 1 a. So, that means the same thing you can obtain from here by writing y a equal to c 1 x minus a, and at y a equal to 0. So, then c 1 x minus a, if it appears here, then c 2 will not comes into the picture. And using the second condition, that is y b, this is again equal to 0, we can find this is equal to lambda times integral a to b b minus s y s ds plus c 1 b, and then for c 2 we can write minus c 1 a, and therefore, from this expression we can find that c 1 equal to lambda divided by a minus b integral a to b b minus s y s ds, and then c 2 equal to minus c 1 a. So, that is equal to minus lambda by a divided by a minus b times integral a to b b minus s y s ds. So, these are two expressions for C 1 and C 2. Now, you can see that for the given problem C 1 and C 2 are all evaluated in terms of lambda a b and this integral involving the unknown quantity y s. If we substitute these expressions into expression for 5, then we can find y x, this is equal to lambda times integral a to x x minus s y s ds. This is the first part. Then for C1 x we will be having lambda x divided by a minus b integral a to b b minus s y s ds, and then minus lambda a divided by a minus b integral a to b b minus s y s ds. So, just look at this expression y x equal to lambda times integral a to x x minus s y s ds plus C 1 x plus C 2. We have obtained C 1 and C 2. So, substituting here we are getting this expression y x equal to lambda times integral a to x x minus s y s ds plus this expression. Now, we have to make some rearrangement. So, this is equal to lambda times integral a to x x minus s y s ds, and in last two integrals the integrand and limit of integrals are all same. So, we can combine them to write lambda times x minus a divided by a minus b integral a to b b minus s y s ds. Now, for simplicity we can absorb the minus sign involved with the second integral in the denominator, that is we can change a minus b to b minus a, and then it will be s minus b. So, making this rearrangement we can write that y x, this is equal to lambda times integral a to x x minus s y s ds plus lambda x minus a divided by b minus a integral a to b s minus b y s ds. Now, our target is to convert this problem into a Fredholm integral equation. Now, in the first integral you can see we have the limit from a to x, but in the second integral we have to the limit a to b. Our target will be to convert this entire expression to an integral involving limit from a to b, and now we have to do some manipulation. This range of integration for the second integral can be divided into two parts. We can introduce one intermediate point x here. So, integral from a to b will be converted into a to x plus x to b. So, introducing that particular subdivision of the range of integration, you can find lambda integral a to x x minus s y s ds plus lambda times x minus a by b minus a integral a to x s minus b y s ds plus lambda x minus a by b minus a integral x to b s minus b y s ds, this expression. Now, combining these two integrals we can write this is lambda times integral a to x then x minus s plus x minus a divided by b minus a multiplied with s minus b y s ds plus lambda times integral x to b. Without any loss of generality we can take the term x minus a by b minus a under the integral sign. We can write this is x minus a times s minus b divided by b minus a y s ds, and after some simple algebra you can able to derive that this will be equal to lambda times integral a to x x minus b times s minus a whole divided by b minus a y s ds plus lambda times integral x to b x minus a then multiplied by s minus b whole divided by b minus a y s ds. So, now you can see we can write this integral as lambda integral a to b some kernel k x comma s y s ds whenever we will be able to define y x into two parts, that is one part of y k x comma s is x minus b times s minus a by b minus a when s is ranging between a to x, and then this kernel is equal to x minus a times s minus b divided by b minus a whenever s is greater than x. So, that means defining this kernel k x comma s, this is equal to, it is defined by x minus b times s minus a divided by b minus a. This definition is valid for a less than equal to s less than x, and this is equal to x minus a times s minus b divided by b minus a, this one where x less than s less than equal to b. So, if we define the kernel in this particular format, then we can write this expression y x equal to sum of these two integrals as y x is equal to lambda times integral a to b k of x comma s y s ds. Now, at this stage, if we try to summarize what we have done just now, we have started with the differential equation d2y dx2 minus lambda y equal to 0 subjected to the boundary conditions y a equal to 0 and y b equal to 0. We have converted this boundary value problem of ordinary differential equation into an integral equation y x equal to lambda integral a to b k x comma s y s ds, where this k x comma s is given by this expression, that means this is the kernel. So, the point is that once we start from a linear homogeneous ordinary differential equation which is a boundary value problem with separated boundary condition, we arrived at a Fredholm integral equation. This is of second kind, and this equation, that integral equation, is also a homogeneous equation. So, this is an important point, you can take note of this, that linear homogeneous ordinary differential equations with boundary conditions, that is separated boundary conditions, can be converted into a Fredholm integral equation of second kind, which is again a homogeneous linear Fredholm integral equation. Now, the point is that if we are able to find out a solution of the given differential equation, that particular solution of the differential equation will satisfy this integral equation and conversely. So, sometimes we can use this integral equation and try to solve this integral equation in order to find out solution of this differential equation and vice versa, depending upon the availability of mathematical tools as well as applicability of the format involved with the problem, that is the nature of kernel and other conditions given for the particular problem. Now, at this point we can try to look at that particular situation, that suppose this integral equation is given. So, whether will it be possible to get back the original differential equation or differential equation corresponding to the given integral equation. And now I am going to show you an example where a given integral equation can be converted into an ordinary differential equation, and we will be able to solve that ordinary differential equation. And after looking at the solution of the ordinary differential equation, we can try to find out some implication and also will be able to make some comments regarding the solution of Freedom integral equation. So, for this purpose we consider the example that y x is equal to lambda times integral 0 to pi k of x comma s y s ds, where the kernel k x comma s, this is given by s times pi minus x whole divided by pi and x times pi minus s whole divided by pi. First definition is for 0 less than equal to s less than x, and second one for x less than s less than equal to pi. So, this is our integral equation. Now, first of all we will be substituting this expression for the kernel into the given integral equation, and after substituting you can find that the limit from 0 to pi have to be divided into two parts, one integral of with limit 0 to x, other integral with limit x to pi, and then we have to apply the Leibniz formula in order to differentiate y x and its derivative. So, we can write this y x is equal to lambda times integral 0 to x k of x comma s y s ds plus lambda times integral x to pi k of x comma s y s ds. So, using the definition for kernel, this will be equal to lambda by pi integral 0 to x s into pi minus x y s ds plus lambda divided by pi integral x to pi x times pi minus s y s ds. So, here we are just substituting the expressions for k x comma s. This is the definition, that is s by pi into pi minus x for s less than x, and x by pi times pi minus s, this is for s greater than x. Now, we apply the Leibniz formula to get dy dx. This is equal to lambda divided by pi times x into pi minus x y x. So, here we are just substituting s equal to x into the integrand, and derivative of x with respect to x is 1. There will be no contribution from the lower limit because it is 0, and then differentiating the integrand with respect to x, we can find plus lambda divided by pi integral 0 to x s into minus 1 y s ds. This is the expression. Then substituting the lower limit into the integrand of the second integral, we can find minus lambda divided by pi x into pi minus x y x, and then differentiating the integrand under integral sign with respect to x partially, we can find x to pi times pi minus s y s ds. And now, you can see these two terms cancels with each other, that is lambda by pi x times pi minus x y x and minus lambda by pi, this one it cancels with each other. So, this is equal to minus lambda divided by pi integral 0 to x s y s ds, this one, plus lambda divided by pi integral x to pi minus s y s ds. On this result we are again going to differentiate with respect to x, and on the right hand side we have to use the Leibniz formula once again. So, using that formula you can find dy dx, this is equal to minus lambda divided by pi x y x minus lambda divided by pi times pi minus x y x. No term with integral sign will come up, because in both of these two integrals integrand are of the variables s only. So, if we differentiate the integrand with respect to x, in both the cases we will be having the result 0, and clearly this minus lambda by pi x y x cancels with plus lambda by pi x y x. So, that means this term cancels with this one. So, then we are left with the expression minus lambda y x, this one, this will be d2 y dx2. So, finally, we are having d2 y dx2 plus lambda y x, this is equal to 0. Now, in order to find out the boundary conditions, we have to use the given problem after substituting the kernels. So, that means we have to again recall the formula, that is y x equal to lambda by pi, this one, y x equal to lambda by pi integral a to x s times pi minus x y s ds plus lambda by pi integral x to pi x into pi minus s y s ds. Here lower limit will be 0, and then if we substitute y 0 here, so then you can see that integral will be from 0 to 0. So, this contributes to be 0, and here in the integrand you have x. So, substituting x equal to 0, this integrand comes out to be 0. So, ultimately we will be having y 0 equal to 0, and similarly if you substitute x equal to pi here. So, first integral vanishes because integrand is identically equal to 0 as it involves pi minus x term. So, substituting x equal to pi, this integrand will be 0. So, no contribution from the first integral, and in the second integral limit is from pi to pi. So, this is also equal to 0. So, we will be having y pi equal to 0. So, that means starting from the given integral equation, we have arrived at the ordinary differential equation d2 y dx2 plus lambda y x, this is equal to 0 with the boundary conditions y 0 equal to 0 equal to y pi. Now, this particular ordinary differential equation is well known for the problems involving eigenvalues and eigenfunctions. So, first of all we solve these equations quickly, because I hope you are familiar with these solutions. So, you can verify for lambda less than 0 or lambda equal to 0, there is no solution other than the trivial solution. So, that means there does not exist any non-trivial solution for lambda less than equal to 0, and for lambda greater than 0 we will be having this y x, that is the general solution. It is given by C1 cosine root over lambda x plus C2 sine root over lambda x, and substituting y 0 equal to 0, we can find this is equal to C 1, because cosine 0 is 1 and sine 0 equal to 0. So, C 1 identically equal to 0, and this implies y x is equal to C 2 sine root over lambda x, and then using the second condition, that is y of pi equal to 0. So, this will be equal to C 2 sine root over lambda pi, and as we are interested for non-trivial solutions. So, that means assuming C 2 not equal to 0, we can find sine root over lambda pi equal to 0. So, this is equal to sine of n pi, where n is equal to 0 plus minus 1 plus minus 2 and so on, and writing the general solution, we can find lambda equal to n square. These are actually eigenvalues, and in this case n equal to 1, 2, 3 and so on, because here minus 1, minus 2, minus 3, all these values will be clubbed with 1, 2, 3 as lambda n equal to n square, and we are not writing n equal to 0 here, because for n equal to 0 lambda n identically equal to 0, and we have already explained that this particular integral equation has no non-trivial solution other than the trivial solution y equal to 0 for lambda equal to 0. So, these are the eigenvalues, and corresponding eigen functions y n x, these are given by C n sin n x, and eigenvalues are lambda n equal to n square, where n equal to 1, 2, 3 and so on. These C n's are actually normalizing factor. In a later lecture, I will be discussing little bit about C n, how this will work for different values of n. So, what we are getting, that this differential equation d2y dx2 plus lambda y equal to 0 with the boundary condition y 0 equal to 0 equal to y pi possesses non-trivial solution for a particular set of values for lambda. If we choose any values of lambda, then solution does not exist, and also solution of the problem is solely linked with lambda. So, that means if we consider the corresponding Fredholm integral equation associated with this boundary value problem, then we have to keep in mind that when we will be having the solution of this problem, we should have the same set of solution. That means solution can be obtained whenever lambda is equal to some n square, n is taking the values 1, 2, 3 and so on, and for particular choice of lambda we will be having the corresponding solution of the form sin n x, and actually here the solution is a linearly dependent with the that is a scalar multiple of sin n x. And now we just verify whether this type of solution satisfies the given integral equation or not for a particular value of lambda. So, for verification we can choose n equal to 2, then lambda 2 is equal to 4, and we are intended to check whether this sin 2 x is a solution to the given problem or not. So, then integral equation becomes y x equal to 4 integral 0 to pi k of x comma s y s ds, and we are going to check whether sin 2 x satisfies this integral equation or not. So, if we consider the right hand side, so this is equal to 4 times integral 0 to x k x comma s sin 2 s ds plus 4 integral x to pi k of x comma s sin of 2 s ds, and this is equal to 4 by pi integral 0 to x pi minus x s sin 2s ds plus 4 divided by pi integral x to pi x times pi minus s sin 2s ds. Of course, this pi minus x can be take outside of the integral sign and x can be take out from the second integral sign, and then using the formula for integrating by parts we can find 4 by pi multiplied with pi minus x, and then integrating we can find s minus cos 2s divided by 2. We are considering this s as u and sin 2s as v. So, this is u integral v dx. So, cos 2s by s, then for by parts formula you will be having 1 minus and integral of sin produces 1 minus. So, this will be plus and then it will be integral cos 2s by 2. So, again integrating we will be having sin 2s divided by 4 and limit will be from 0 to x, and for the second part we will be having 4x by pi outside the integral sign, and then we have minus pi minus s cosine 2s divided by 2, and then it will be minus sin 2s divided by 4 limit from x to pi. This minus sign is coming here because for first integration, that is integral v ds, we will be having 1 minus. For by parts formula we will be having another minus, and derivative of pi minus s with respect to s will produce another minus 1. So, ultimately sign will be minus because integral of cosine does not affect the sign just appearing before this integral, and after substituting this limit and after some simplification you will be able to verify that this is comes out to be simply sin 2x. So, that means the function y x equal to sin 2x satisfies this integral equation, and therefore, the solution of the given problem is solely linked with the eigenvalues, and there is no non-trivial solution whenever lambda takes the values other than 1, 4, 9, 16, 25 and onwards, that is square of the positive integers. So, this point we have to keep in mind that most of the time we will be having this type of solutions, and we will be discussing these things with the light of Sturm-Liouville boundary value problem in details. Now, before going to that part, now I am going to consider that a general second order linear ordinary differential equation, which is a non homogeneous ordinary differential equation with the specified separated boundary condition, can be converted into a Fredholm integral equation, and you can see that when we convert it, then we will be having a Fredholm integral equation of second kind which is non homogeneous. So, for this purpose we consider the equation d2y dx2 plus a1 x dy dx plus a2 x y, this is equal to g x, where given conditions are y a equal to alpha, y b equal to beta. These are the boundary conditions. So, first of all, integrating the given differential equation, we can find dy dx, that is equal to integral a to x gs ds minus integral a to x a1 s d of y s minus integral a to x a2 s y s ds plus c1, because dy dx at x equal to a is not known. So, we are writing c1 here, and in order to write the middle integral, we have used the notion that dy ds operated with ds produces dys, and here after using the by parts formula we can get this is equal to ax gs ds minus a1x yx this one plus a1a multiplied with alpha, because y a equal to alpha here, minus integral plus integral a to x a 1 dashed s y s ds minus integral a to x a 2 s y s ds plus c 1. So, this is the expression for dy dx. If we integrate it again, then we will be having y x minus alpha is equal to integral a to x, then integral a to s g of s 1 ds 1 minus integral a to x a 1 s y s ds plus a 1 a alpha times x minus a plus integral a to x, then integral a to s a 1 dashed s 1 y s 1 d s 1 minus integral a to x integral a to s a 2 s 1 y s 1 d s 1 plus c 1 times x minus a. Here for little bit simplicity I am substituting limit here without going to introduce a 1 x plus c 2 here, and again here we can apply the formula, that is fundamental reduction formula to successive reduction formula to convert this double integral into second integral, and we will be having y x minus alpha is equal to integral a to x x minus s g s ds minus integral a to x. There is no need to apply that formula here at a 1 s y s ds, then plus a 1 a alpha times x minus a remains unaltered, and last two integrals will be a to x, then x minus s a 1 dashed s y s ds minus a to x x minus s a 2 s y s ds, and last term will remain unaltered c 1 times x minus a. Now, in this expression only unknown quantity is c 1 that we have to evaluate, and in order to find out c 1 we are substituting x equal to b, and we can utilize the condition y b equal to beta. So, using this substitution into this integral we will be having beta minus alpha, this is equal to integral a to b, then b minus s g s ds minus integral a to b a 1 s y s ds plus a 1 a alpha times b minus a plus integral a to b b minus s a 1 dashed s y s ds minus integral a to b b minus s a 2 s y s ds plus c 1 times b minus a. So, ultimately we will be having this c 1 is equal to beta minus alpha divided by b minus a, that is beta minus alpha divided by b minus a, and then this entire quantity we have to shift onto the left hand side, and then interchanging the left hand and right hand, all this expression will be having a minus 1 factor at the beginning. So, then it will be minus 1 by b minus a with the expressions, that is a to b, b minus s, g s d s, starting from this one minus dot dot up to the last expression integral a to b, b minus s, a to s, y s d s. So, now we have to substitute this expression for C 1 into here, that is y x minus alpha is given by this expression. So, if we call this as 1 and this expression for C 1 this as 2. So, we can write that substituting for C 1 from 2 in 1 we get. Now, this is going to be a gigantic expression, but step by step we can try to write it down. Y x equal to alpha plus. So, first of all we are transferring this alpha onto the right hand side, then we have to write this entire expression, and then plus x minus a will be multiplied with the expression for C 1. So, writing these terms we can find this will be integral a to x, x minus s, g s d s, then minus integral a to x, a 1 s, y s d s, plus a 1 a alpha times x minus a, plus integral a to x, x minus s, a 1 dashed s, y s d s, minus integral a to x, x minus s, a to s, y s d s, plus x minus a multiplied with the formula for C 1, that is the expression for C 1, not formula, that is beta minus alpha by b minus a minus 1 by b minus a integral a to b, b minus s, g s d s, plus 1 by b minus a integral a to b, a 1 s, y s d s, minus a 1 a times alpha minus 1 by b minus a integral a to b, b minus s, a 1 dashed s, y s d s, and finally plus 1 by b minus a integral a to b, b minus s, a to s, y s d s, this one. Now, this x minus a times minus a 1 alpha a will cancels with this one. So, that means these two terms, this one and this one cancels with each other, and now our target will be to separate the integral involving y s term and the terms free from y s. So, if we do that, then we will be having one expressions, that is alpha plus integral a to x, x minus s, g s d s, plus x minus a divided by b minus a, then beta minus alpha minus integral a to b, b minus s, g s d s, this one, and then plus we will be having 6 terms, that is x minus a divided by b minus a integral a to b, a 1 s, y s ds, and now I am writing the similar terms side by side, then we will be having this term. So, that is this is this term, and then minus integral a to x a1 s y s ds, then other 4 terms plus integral a to x x minus s a1 dash s y s ds minus x minus a divided by b minus a integral a to b b minus s a 1 dash s y s ds plus x minus a by b minus a integral a to b b minus s a 2 s y s ds minus a to x x minus s a 2 s y s ds. Now, these particular terms, that is already we have written here, if we marked with this some particular color, that is alpha plus this integral this particular expression constitutes our f x. So, then y x will be equal to f x plus, we can put it into the form a to b k x comma s y s ds, where expression for f x is given earlier. Now, we have to look at this, how we can find out this k s comma x comma s, and idea is that as we have done earlier, every integral of a to b have to be divided into 2 parts, that is a to x and x to b. Then after rearranging the terms, we can get this results, that is x minus a divided by b minus a integral a to b a 1 s y s ds minus integral a to x a 1 s y s ds, and if we use this result, that is 1 equal to x minus a minus x minus b divided by b minus a, then we can find this will be equal to x minus a divided by b minus a integral x to b a 1 s y s ds plus x minus b divided by b minus a integral a to x a 1 s y s ds. And for rest of the parts, we can take this a 1 dash s minus a 2 s as common term, then rest of the part can be written as x minus a divided by b minus a integral a to b b minus s times a 2 s minus a 1 dash s y s ds, this minus integral a to x x minus s times a 2 s minus a 1 dash s ds, this can be written as equal to x minus a divided by b minus a integral x to b b minus s a 2 s minus a 1 dash s y s ds plus x minus b divided by b minus a times integral a to x a minus s times a 2 s minus a 1 dash s ds. So, this one. So, we will be able to arrive at this stage, and now combining this result, we can define that the kernel of the integral equation k x comma x, this is given by x minus b divided by b minus a times a 1 s minus a minus s times a 1 dash s minus a 2 s, this one, this is valid for a less than equal to s less than x, and then x minus a divided by b minus a times a 1 s minus b minus s times a 1 dash s minus a 2 s, this one for x less than s less than equal to b. And you can check from the previous integral, we will be having for a to x range x minus b by b minus a 1 s, that is appearing here, and then from this part, that is a to x, it will be x minus b by b minus a multiplied with minus a minus s times a 1 dash s minus a 2 s. So, this is the expression for s less than x, and the next one, that is x minus a by b minus a equal to a 1 s minus b minus s, this one. So, this is the kernel. So, with this kernel we can convert a general second order linear non homogeneous boundary value problem to a Fredholm integral equation, linear integral equation of second kind, and of course, this is a non homogeneous Fredholm integral equation. So, this lecture I can end at this point. In next few lectures, I will be considering the concept of Green's function, that is very much important to obtain the solution for non homogeneous linear boundary value problem, and Sturm-Liouville theory, which will be required to understand the solution methods for Fredholm integral equation. Thank you.